Before there were constellations traced across the night sky, before galaxies wheeled in vast spirals of light, before planets cooled and oceans formed, there was a universe without stars. Not darkness as we understand it, not the dimming of evening or the shadow cast by a mountain, but an absence so complete that light itself did not yet exist. 13.8 billion years ago, the universe began expanding from an unimaginably hot and dense state. In its earliest fraction of a second, energy and matter were indistinguishable. Space itself stretched faster than comprehension, and the foundations of physics as we know them were forged. As the cosmos expanded, it cooled. Within minutes, the first atomic nuclei formed, hydrogen and helium the simplest and lightest elements. Yet for hundreds of millions of years after the beginning, no stars shone. The universe entered what astronomers call the cosmic dark ages, a vast and silent expanse filled almost entirely with diffuse hydrogen gas. There were no galaxies yet, no planets, no luminous beacons piercing the void. Only faint ripples in density, tiny variations left over from the universe's birth, subtly shaped the distribution of matter. Billions of years later, spacecraft such as the Planck satellite would map the faint afterglow of that primordial era, revealing that those minute fluctuations, smaller than one part in 100,000, were the seeds of everything that followed. Gravity, patient and relentless, began to amplify those tiny differences. Over millions of years, immense clouds of hydrogen and helium formed, each spanning hundreds of thousands of light years and containing more mass than entire galaxies would one day hold in stars. Within these clouds, pressure began to rise as atoms collided more frequently and temperature slowly climbed. For the first time, conditions approached the threshold needed for nuclear fusion. Hydrogen nuclei, normally repelled by their electrical charges, were forced close enough together for fusion to occur. Helium formed in tiny quantities and energy burst outward for the first time. Light had entered the universe, faint, scattered, yet unstoppable. The first stars ignited, and with them came the end of the cosmic darkness. These first stars were enormous, some hundreds of times the mass of our sun. Without heavier elements to cool, the gas clouds could not fragment efficiently, forcing the creation of these massive beacons. Their brilliant blue-white light shone across the void, brief but astonishing, illuminating their surroundings and forever altering the universe. Inside these primordial giants, nuclear fusion progressed rapidly. Hydrogen fused into helium, helium fused into carbon, carbon into oxygen, oxygen into heavier elements. These processes forged the first chemical complexity in the cosmos, planting the seeds for everything to come: planets, atmospheres, life itself. Yet the very mass that made these stars so luminous also made their lives fleeting. A star's mass dictates its fate. Greater mass requires higher pressure and temperature to counteract gravity, consuming fuel more rapidly and ending life in a matter of millions rather than billions of years. When the largest stars reached iron in their cores, fusion could no longer produce outward energy. Gravity claimed victory. In a fraction of a second, the core collapsed. The implosion rebounded in an unimaginably violent explosion, a supernova that briefly outshone entire galaxies. These first supernovae enriched space with carbon, oxygen, silicon, and iron. The death of one generation of stars paved the way for the next. These heavier elements allowed clouds to cool more efficiently, forming smaller, longer-lived stars. Over billions of years, clusters of stars merged into larger systems. Galaxies began to spin, taking on shapes that we now recognize: spirals, ellipticals, and irregular collections of stars. Among them, a barred spiral emerged, the Milky Way, destined to host our sun. In its infancy, the Milky Way was chaotic, filled with supernova shockwaves, swirling clouds of gas, and regions of intense star formation. Within the spiral arms of galaxies, molecular clouds cooled and fragmented. Gravity concentrated regions into dense cores. Protostars formed, surrounded by disks of gas and dust. Jets of plasma erupted from the poles, clearing paths through the clouds. Each protostar endured hundreds of thousands of years of contraction until the core temperature reached 10 million degrees Celsius. Hydrogen fusion began, and a star ignited, achieving hydrostatic equilibrium. This balance, fusion pushing outward against gravity pulling inward, defines the life of a stable star. Approximately 4.6 billion years ago, one such molecular cloud collapsed under the influence of a nearby supernova shockwave. At its center, our sun ignited. The surrounding disk flattened, forming planetesimals that merged into planets. Rocky planets took shape near the sun. Gas giants accreted farther away. On one small world, conditions allowed water to pool, forming oceans. Earth emerged, still molten, gradually cooling under the steady energy of its star. Our sun, ordinary by galactic standards, fused 600 million tons of hydrogen into helium every second, converting millions of tons of mass into energy radiated across space. Photons generated in the core took hundreds of thousands of years to reach the surface, then traveled 8 minutes to reach Earth. Every beam of sunlight touching your skin began as nuclear fire deep within the sun, a reminder of the extraordinary processes that sustain life. Stars are not uniform. Red dwarfs, small and dim, burn slowly, sustaining life for trillions of years. Massive blue giants burn fiercely and briefly, shaping their surroundings with intense ultraviolet radiation before exploding in supernova. The mass of a star dictates its temperature, brightness, lifespan, and ultimate fate. Binary systems, where two stars orbit one another, exhibit further complexity. Stars can exchange mass, spin rapidly, or end their lives in spectacular events like Type Ia supernova, which standardize brightness for cosmological measurements. Even after death, stars continue to shape the universe. Neutron stars emerge from core collapse, spinning rapidly as pulsars sending beams of radiation across space like cosmic lighthouses. Black holes form when the most massive stars collapse beyond the limits of neutron degeneracy, bending spacetime itself and swallowing light. Creation and destruction are intertwined. The universe's history is a cycle of stellar birth, life, and death, each generation seeding the next. From the darkness before the first stars to the birth of our sun, the cosmos transformed into a luminous, structured universe. Galaxies rotate, nebulae glow with new stars, and molecular clouds continue to collapse even now, forming stars that will shine millions or billions of years from today. The cycle continues. Hydrogen fuses into helium, elements build, stars die, and new stars ignite. Stars are more than distant points of light. They are the engines of creation, the forges of chemistry, and the architects of planetary systems. They give the universe continuity, order, and energy. Every sunrise, every beam of light, is a direct product of stellar processes that began billions of years ago. The story of stars extends beyond simple fusion. Inside the core of a star, extreme pressure and temperature strip electrons from atoms, creating plasma, an electrically charged, highly conductive gas. Photons generated by fusion collide countless times in the radiative zone, a region so dense that light may take hundreds of thousands of years to escape. In the outer convective zone, currents of rising and sinking plasma carry energy outward, producing granules and turbulence visible at the surface. The photosphere, the layer from which light finally radiates into space, is what we perceive as the glowing star. Magnetic fields twist and tangle across the surface, creating sunspots, flares, and coronal mass ejections. Even a seemingly calm star is alive with motion, energy, and magnetic activity. Stars also shape their environments. Stellar winds push gas and dust into space, carving bubbles and nebulae. Ultraviolet radiation ionizes surrounding hydrogen, creating H Roman 2 regions that glow with characteristic colors, revealing the locations of star formation. The life of a star is inseparable from the galactic ecosystem it inhabits. Supernovae seed the interstellar medium with heavy elements, enriching subsequent generations of stars and planets. Each cycle of birth and death increases chemical diversity, building the potential for rocky worlds, atmospheres, oceans, and life. Some stars form in isolation, quietly burning for billions of years. Others form in dense clusters, their lives intertwined with dozens, hundreds, or thousands of neighboring stars. In binary or multiple systems, mass transfer can dramatically alter a star's evolution, triggering nova outbursts or accelerating the journey towards supernova. In globular clusters, ancient stars preserve a record of the galaxy's early history, providing astronomers with clues to the universe's formative epochs. Even the smallest stars have importance. Red dwarfs, though faint, dominate the stellar population of galaxies. They burn hydrogen so slowly that some may exist for trillions of years, long after more massive stars have perished. Blue giants, in contrast, live fast and die young, their intense radiation sculpting into stellar clouds and enriching the cosmos in a relatively short cosmic instant. Each star, regardless of mass, contributes to the dynamic balance of galaxies and the broader evolution of the universe. From the first ignition of hydrogen in a primordial star to the formation of our Sun, from the turbulent nebulae of young galaxies to the serene burning of ancient red dwarfs, stars define the cosmos. They are engines of light, timekeepers of cosmic history, and the crucibles from which the universe builds complexity. Every atom heavier than helium owes its existence to the life and death of stars. Every planet, every ocean, every living cell is a product of processes that began billions of years ago in the cores of distant suns. In this sense, to understand stars is to understand the universe itself, its history, its structure, and the potential for life. And so, the first light ended the darkness, initiating an eternal cycle of creation, fusion, and renewal that continues to this day. Somewhere, even now, new stars are forming, lighting the cosmos in ways both subtle and spectacular, carrying the legacy of all those that came before. Every photon, every glimmer in the night sky tells a story of gravity, pressure, fusion, and time, a story that continues unbroken through the vast reaches of space and the ages of cosmic history. Beyond ordinary stars lie the universe's most extreme objects, where the laws of physics are pushed to their limits.
Neutron stars, the dense remnants of massive stellar collapse, cram more mass than our Sun into a sphere barely 20 kilometers across. A single teaspoon of neutron star material weighs billions of tons. Some spin hundreds of times per second, generating magnetic fields trillions of times stronger than Earth's.
These spinning neutron stars emit beams of radiation detectable as pulsars, cosmic lighthouses that mark precise intervals, some more accurate than atomic clocks.
Magnetas, a rare subclass of neutron stars, amplify these extremes. Their magnetic fields distort atomic structures, trigger bursts of gamma rays, and produce starquakes in their crusts.
These stellar remnants are laboratories for physics that cannot be reproduced on Earth, revealing the behavior of matter under incomprehensible density and pressure.
Even black holes, the ultimate endpoint for the most massive stars, continue the story of stellar influence. Black holes warp space-time itself, siphon matter from companion stars, and power energetic jets that can extend thousands of light years into space, shaping their galactic neighborhoods.
Stars are factories of elements, but they are selective. The lightest elements, hydrogen, helium, and traces of lithium, were formed in the Big Bang.
Heavier elements arise only through stellar nucleosynthesis. Hydrogen fuses into helium, helium into carbon,
And oxygen,
carbon into neon,
and magnesium,
oxygen into silicon,
and sulfur.
silicon into iron.
Each stage requires higher temperatures and shorter timescales, with iron marking the energetic limit. Beyond iron, fusion consumes energy rather than producing it, making gravitational collapse inevitable for massive stars.
Supernova then distribute these elements, enriching the interstellar medium and allowing planets with rocky surfaces, atmospheres, and potentially life to form.
Population remnant 3 stars, the universe's first generation, were massive and short-lived, composed almost entirely of hydrogen and helium.
Their violent deaths seeded later generations with metals, enabling population Roman 2 and eventually population I stars, the stars familiar in modern galaxies, including our Sun.
Metallicity effects of stars, opacity, internal convection, and eventual evolution.
Stars born in low metal environments are hotter, bluer, and more massive.
Those in high metallicity regions, like the spiral arms of the Milky Way, are cooler, more stable, and often host planetary systems.
Stellar clusters provide snapshots of galactic history.
Open clusters, loose collections of young stars, reveal ongoing star formation.
Globular clusters, ancient, dense spheres containing hundreds of thousands of stars, preserve records of the early universe. By studying their composition and distribution, astronomers reconstruct the galaxy's formation, tracing the cycles of stellar birth, death, and enrichment that have shaped the Milky Way over billions of years.
Variable stars are another window into the inner workings of stars.
Cepheid variables pulsating giants expand and contract with rhythmic precision.
The period luminosity relationship allows astronomers to measure cosmic distances, calibrating the scale of the universe itself.
RR Lyrae stars, smaller and older, reveal ancient galactic populations, while mirror variables, red giants pulsating with extreme brightness changes, demonstrate the final stages of stellar evolution from medium-mass stars. Supernova remnants, the echoes of stellar death's shape interstellar space. Expanding shells of gas compress nearby clouds, triggering star formation in successive generations. The Crab Nebula, the remnant of a supernova observed in 1054 CE, continues to radiate energy, powered by a rapidly spinning neutron
Star at its center. Each remnant is both a tomb and a seabed, preserving the memory of the exploded star while planting the chemical ingredients for the future.
Stars influence galactic dynamics beyond chemistry. Their collective gravity stabilizes spiral arms, drives rotation curves, and interacts with dark matter halos. Massive stars' radiation pressure sculpts interstellar clouds into pillars, arcs, and cavities. Supernova-driven shockwaves ripple across the galactic disk, compressing clouds and triggering sequential waves of star formation. Stellar populations, in effect, are both the product and the architects of their galaxies. Exotic binary systems showcase stellar extremes. Contact binaries share envelopes exchanging mass and energy. X-ray binaries, where a neutron star or black hole accretes material from a companion, generate intense X-ray radiation observable across millions of light years.
Nova eruptions caused by accreted hydrogen igniting on a white dwarf's surface periodically brighten stars to extraordinary luminosities.
Type
I supernova, triggered by similar processes, provide standard candles essential for measuring cosmic expansion. Stars are the universe's chronometers. Their lifespans dependent on mass range from millions to trillions of years.
High-mass stars burn fuel rapidly, living briefly, but shaping galaxies profoundly. Low-mass stars burn slowly, quiet, and enduring. preserving the chemical history of their regions.
In clusters, stars of similar age but different mass illustrate the predictable sequence of stellar evolution known as the Hertzsprung-Russell diagram, a fundamental tool in astrophysics. Stellar winds and outflows are subtle but powerful. Even relatively stable stars emit particles that sculpt nearby nebulae. Massive stars' winds drive turbulence in molecular clouds, compressing regions to trigger new star formation. Wolf-Rayet stars in their final evolutionary stages shed enormous mass, enriching their surroundings with carbon, nitrogen, and oxygen. Planetary nebulae, the final breaths of medium-mass stars, illuminate interstellar space with intricate, luminous shells, evidence of the star's final acts of creation.
The interplay between stars and their surroundings is continuous.
Stars are born, evolve, die, and in death enrich the environment for new stars. Stellar populations create feedback loops regulating the rate of star formation in galaxies. Chemical enrichment, energy deposition, and gravitational dynamics all depend on the life cycles of stars, making them central to cosmic evolution.
Even the smallest stars, red dwarfs, play crucial roles. Though faint, they dominate galactic populations.
Their longevity exceeds the current age of the universe, meaning none have yet exhausted their fuel.
They quietly preserve the record of galactic evolution, slowly radiating energy, maintaining stability in stellar neighborhoods, and potentially hosting planets in long-term habitable zones. Stellar formation is ongoing.
Across the Milky Way, molecular clouds collapse, forming protostars that will shine for millions or billions of years. Regions like the Orion Nebula, the Carina Nebula, and the Eagle Nebula showcase the dynamic interplay of gravity, radiation, and magnetic fields, producing new stars in spectacular cosmic nurseries.
These regions demonstrate that star formation is not confined to the distant past. It is a continuing, universal process.
In the next millions of years, new stars born today will follow the same patterns: fusion in cores, life cycles dictated by mass, eventual death as white dwarfs, neutron stars, or black holes, and the dispersal of elements into the galaxy. The cycle of stellar birth, life, death, and rebirth continues endlessly, connecting the earliest stars to those forming now, and linking all matter in the universe through shared cosmic ancestry.
Some stars stand as titans among their peers, remarkable not just for luminosity, but for the extremes they reveal.
Rigel, a blue supergiant in Orion, burns tens of thousands of times brighter than the sun, radiating ultraviolet light that shapes surrounding nebulae. Antares, a red supergiant in Scorpius, swells hundreds of times the sun's radius, its outer layers tenuous and turbulent, destined to end in a spectacular supernova. Sirius, the brightest star in the night sky, is a binary system, a main sequence star paired with a white dwarf, exemplifying the diversity and complexity of stellar relationships.
Each star is a laboratory, a testament to the interplay of mass, age composition, and environment.
Nebulae, the cradles of stellar birth, illuminate the profound connection between stars and their surroundings.
In the Orion Nebula, dense pockets of gas collapse under gravity, giving rise to newborn stars whose ultraviolet light ionizes surrounding hydrogen, producing brilliant red and pink glows.
The Carina Nebula, home to Eta Carinae, exhibits colossal pillars sculpted by radiation and winds from massive stars, revealing the turbulent processes that drive star formation. The Eagle Nebula's pillars of creation capture the imagination as gravity concentrates matter, while light from nearby stars carves channels through dense clouds. These cosmic nurseries show that star formation is both creative and destructive, a balance of forces that shapes the galaxy's luminous tapestry.
Within stars, nucleosynthesis extends beyond simple hydrogen and helium fusion.
The S process, slow neutron capture, occurs primarily in red giants, producing elements like strontium, barium, and lead over thousands of years. The R process, rapid neutron capture, occurs during supernova, forming half of the elements heavier than iron, including gold, platinum, and uranium.
The P process, a rarer pathway, produces proton-rich isotopes.
These processes ensure that every atom of matter heavier than helium, every planet, every ocean, every living organism owes its existence to the life cycles of stars. Each generation of stellar birth and death enriches the cosmos, creating chemical diversity that allows planets to form and life to emerge. Binary and multiple star systems introduce further complexity. In closed binaries, mass transfer can rejuvenate one star while accelerating the death of its companion.
Nova, resulting from hydrogen accumulation on a white dwarf, provide episodic bursts of luminosity observable across galaxies.
Type Ia supernova, arising from similar processes, are critical for measuring cosmic distances, linking stellar physics to cosmology.
In triple or higher order systems, gravitational interactions can eject stars into interstellar space, producing runaway stars that traverse galaxies at extraordinary speeds.
These dynamics highlight the interconnectedness of stars, where the fate of one is often bound to the fate of others. Stellar evolution also shapes galactic chemistry and structure. Massive stars enrich their environments rapidly, influencing subsequent generations of stars. Low-mass stars preserve chemical signatures over billions of years, allowing astronomers to reconstruct the history of the Milky Way.
Metallicity gradients across galaxies, with younger, high metallicity stars in spiral arms and older, low metallicity stars in bulges and halos, provide a record of star formation and chemical evolution.
Through these processes, stars are both the authors and archivists of cosmic history. Exotic stars push the limits of known physics.
Wolf-rayet stars, losing mass at phenomenal rates, produce strong stellar winds and enrich their surroundings with heavy elements.
Luminous blue variables like Eta Carinii undergo violent eruptions temporarily exceeding millions of times the sun's brightness. Pulsars, spinning neutron stars emitting regular beams of radiation, serve as natural timekeepers and probes of extreme density and magnetism. Magnetars, with magnetic fields trillions of times stronger than Earth's, demonstrate the violent potential of stellar remnants. Even black holes, though invisible, are consequences of stellar life cycles, shaping galaxies through gravity and energetic jets that extend far beyond their origin. Galaxies themselves are shaped by the stars within them. Star formation regulates galactic evolution, while supernova-driven winds redistribute gas and metals, influencing future star formation. Stellar populations, whether in open clusters, globular clusters, or the galactic disk, provide snapshots of history.
Observing clusters of different ages and metallicities allows astronomers to piece together timelines stretching billions of years.
Stars are simultaneously actors and chroniclers, influencing structure while preserving evidence of the past.
The universe's chemical evolution hinges on stellar cycles. Each supernova distributes elements forged over millions of years, seeding clouds that will form planets and life. Carbon, oxygen, nitrogen, iron, and heavier elements all trace their origins to the fusion furnaces of stars. The presence of these elements in our solar system reflects billions of years of stellar processing, linking every atom in our bodies to stars that lived and died long before Earth existed. In interstellar space, the remnants of stars continue to interact with their environment. Supernova remnants like the Crab Nebula expand at thousands of kilometers per second, compressing surrounding gas and triggering new star formation. Planetary nebulae illuminate space with glowing shells of material ejected by dying medium-mass stars, showcasing intricate patterns shaped by stellar winds, magnetic fields, and binary interactions. These structures are monuments to stellar life cycles, both memorializing the past and shaping the future. Stars are not static entities. They pulsate, rotate, and interact dynamically with companions and surroundings. Their magnetic fields produce flares and mass ejections. Their energy drives the evolution of molecular clouds, their winds shape nebulae, and their deaths seed future generations.
Each star, regardless of mass or lifespan, contributes to the ongoing narrative of the galaxy,
The interplay of matter,
energy, and gravity that defines cosmic evolution.
even the quiet, long-lived red dwarfs, small and dim by comparison to giants, dominate stellar populations. Their slow fusion and stability make them cosmic anchors, preserving chemical signatures and sustaining planetary systems over trillions of years. While their light is faint, their cumulative impact across billions of stars shapes galactic evolution subtly but profoundly. The cycle of stars is eternal. Clouds collapse, stars ignite, life cycles progress according to mass and composition, and death enriches the medium for new stars. Galaxies filled with countless stars are arenas of creation and destruction, each star a narrative of energy, matter, and time. From the first massive population Roman 3 stars to the ongoing birth of stars in Orion, Carina, and beyond, the cosmos remains a stage for stellar evolution, a continuous story of fusion, light, and transformation. Through observation, simulation, and theory, humans have begun to decode these processes. Telescopes capture light across the electromagnetic spectrum, from radio waves emitted by cold molecular clouds to gamma rays from supernova remnants. Neutrino detectors probe cores of active stars. Gravitational wave observatories reveal the mergers of neutron stars and black holes, events that send ripples through space-time itself.
Every instrument provides insight into the ongoing drama of stars, revealing their structure, life cycles, and profound influence on the universe.
In sum, the hearts of fire that burn across the Milky Way and beyond are more than mere points of light. They are engines of creation, laboratories of extreme physics, authors of chemical evolution, and architects of galaxies. Every supernova, pulsar, and planetary nebula is a chapter in the story of the cosmos, linking the birth of stars to the formation of planets and the eventual emergence of life. To understand stars is to understand the universe itself, its history,
its structure, and the dynamic processes that continue to unfold across billions of years and light years of space.
The story of stars cannot be separated from the galaxies that host them. Galaxies are cosmic cities, vast collections of stars, gas, dust, and dark matter bound together by gravity. They range from dwarfs containing a few billion stars to giants housing trillions, spinning in spirals, forming ellipses, or existing in irregular, chaotic arrangements. Within these stellar metropolises, stars are born, live, and die, interacting with one another and with the surrounding interstellar medium. Galaxies themselves evolve over billions of years, shaped by mergers, starbursts, and the collective life cycles of their stellar populations. Spiral galaxies like our own Milky Way are perhaps the most visually iconic. They possess sweeping arms that radiate from a central bulge filled with both young, massive stars and dense clouds of gas and dust.
In these arms, star formation is ongoing, as gravitational instabilities and shock waves compress gas clouds, igniting fusion in newborn stars.
The central bulge, dominated by older, more metal-rich stars, preserves a record of ancient star formation, a living archive of the galaxy's past. Spiral galaxies are dynamic systems, their rotation curves revealing the influence of unseen dark matter halos that dominate the mass of the galaxy and govern its motion. Elliptical galaxies tell a different story. They are more spherical or elongated, containing mostly old stars with little ongoing star formation. Gas has long since been consumed or expelled, leaving a stellar population that quietly ages. Despite this apparent tranquility, elliptical galaxies are often the product of galactic mergers, cosmic collisions that trigger bursts of star formation and redistribute stars and gas. These galaxies are laboratories for understanding the long-term evolution of stars in dense environments and the processes by which galaxies grow and transform over time. Irregular galaxies lacking symmetry or uniform structure provide insight into the chaotic side of cosmic evolution, often the result of gravitational interactions or mergers. These galaxies are rich in gas and dust, with star formation occurring in scattered clusters. Despite their disorderly appearance, irregular galaxies are crucial to understanding how stars form under extreme conditions, how galactic interactions shape stellar populations, and how cosmic environments influence the life cycles of stars. Star formation within galaxies is both a local and global phenomenon. Molecular clouds, vast cold regions of gas and dust, serve as stellar nurseries. Within these clouds, gravity pulls matter into dense cores, forming protostars that eventually ignite fusion. Stellar feedback, winds, radiation, and supernova can either inhibit or trigger subsequent star formation, creating complex patterns across galactic disks. Starburst regions, like those in the Whirlpool Galaxy or M82, exhibit intense, concentrated star formation, producing massive clusters and altering the chemical and dynamical properties of the galaxy itself.
Galactic structure is intimately linked to the types of stars they contain.
Population: a star's metal-rich and relatively young populate spiral arms and disks, often hosting planetary systems. Population: Roman II stars, older and metal-poor, reside in halos, bulges, and globular clusters, providing clues to the early epochs of star formation.
The elusive population Roman III stars, the first generation after the Big Bang, were massive and short-lived, leaving no surviving examples today, but influencing subsequent star formation by enriching the primordial gas with metals.
These stellar populations allow astronomers to trace galactic evolution from the earliest formation stages to the present day.
Supernova and stellar winds play a crucial role in galactic ecology. Massive stars inject energy and momentum into the interstellar medium, shaping molecular clouds, driving turbulence, and triggering new generations of stars. Type Roman II supernova disperse elements like carbon, oxygen, silicon, and iron, ensuring that later stars and planets contain the ingredients for complex chemistry. Type I supernova, standard candles of cosmology, illuminate the structure of the universe and measure its expansion, linking stellar evolution to cosmic scale dynamics. Star clusters provide microcosms of galactic processes. Open clusters, young and loosely bound, demonstrate ongoing star formation and chemical homogeneity. Globular clusters, dense and ancient, preserve stellar populations from the early universe, allowing astronomers to probe chemical evolution and stellar dynamics over billions of years. Observing these clusters across multiple galaxies reveals patterns in star formation efficiency, metallicity, and the effects of galactic environment on stellar evolution. Nebulae, the glowing, diffuse clouds of gas and dust, reveal the interplay of stars and their surroundings.
H Roman 2 regions, ionized by young massive stars, emit bright ultraviolet radiation, creating vivid nebula colors. Supernova remnants, expanding shells of enriched gas, compress nearby clouds, initiating new waves of star formation. Planetary nebulae, the final breaths of dying stars, illuminate the interstellar medium, with intricate symmetric patterns showcasing the final contributions of medium-mass stars to galactic evolution. Galactic mergers are pivotal events reshaping stellar populations and triggering bursts of star formation.
When two spiral galaxies collide, tidal forces funnel gas into central regions, igniting starbursts and feeding supermassive black holes.
Elliptical galaxies often result from such mergers, their stars redistributed into more spheroidal structures. These interactions highlight the interconnectedness of stars and galaxies, showing that the life cycle of stars is not only a local process, but also a cosmic one, influenced by the vast gravitational dance of galaxies. Within galaxies, the distribution of stellar masses, the initial mass function, dictates the types of stars that dominate and the rate of chemical enrichment. Massive stars, though rare, dominate energy output and nucleosynthesis, while the vast majority of stars are low mass, contributing to galactic structure and chemical preservation over trillions of years. This balance shapes the evolution of galaxies, determining how quickly they consume gas, how they produce heavy elements, and how they interact with neighboring systems. Cosmic feedback is central to galaxy evolution. Radiation from massive stars, supernova-driven shock waves, and stellar winds collectively regulate star formation. Too little feedback allows unchecked collapse of gas clouds, producing intense bursts of star formation and rapid gas depletion. Too much feedback disperses gas, inhibiting the formation of new stars. Galaxies maintain a delicate balance orchestrated by the collective influence of their stars, where each generation sets the stage for the next.
Even isolated stars have galactic significance.
Runaway stars, ejected by gravitational interactions or supernova, traverse the interstellar medium at incredible velocities, interacting with gas clouds along the way. Their winds and radiation shape clouds far from their birthplace, seeding regions with energy and momentum.
Stellar remnants, white dwarfs, neutron stars, black holes continue to influence galactic dynamics long after their parent stars die.
Binary systems, especially those with compact remnants, provide energy and radiation that can affect star formation and the evolution of nearby systems. Extragalactic observations show the universality of these processes.
Spiral arms in Andromeda mirror those in the Milky Way, with massive young stars and star-forming regions punctuating dusty lanes.
Starburst galaxies such as M82 illustrate extreme feedback and intense star formation.
Globular clusters in the halos of distant galaxies preserve ancient stellar populations,
allowing astronomers to compare galactic histories across cosmic time. These observations confirm that the process is shaping stars and their environments are consistent, yet scaled by mass density and galactic context. Stars are also central to understanding cosmic evolution. The light emitted by stars dominates the observable universe, carrying information about distance, age, chemical composition, and motion. Spectroscopy reveals the fingerprints of elements, allowing astronomers to reconstruct the history of nucleosynthesis across galaxies. Photometry tracks stellar populations, star formation rates, and the progression of galactic evolution. Each observation, from individual stars to entire galaxies, contributes to a unified picture of the cosmos, highlighting the role of stars as both agents and chroniclers of cosmic history.
The diversity of stellar environments also shapes planetary systems. Stars in dense clusters face higher rates of close encounters, which can disrupt protoplanetary disks and planetary orbits. Stars in isolated regions retain their disks longer, allowing planets to form in stable configurations.
The metallicity of a star influences planet formation. Metal-rich stars are more likely to host rocky planets, while metal-poor stars may produce gas giants or lack planets entirely. The interplay between stars and their environments thus has profound implications not just for stellar evolution, but for the emergence of planets and the potential for life. Across cosmic time, the patterns of star formation reveal the history of the universe.
In the first billion years, massive metal-poor stars dominated, burning brightly and enriching the primordial gas.
Later, star formation shifted to more moderate masses, producing longer-lived stars capable of hosting planets. Observing distant galaxies allows astronomers to look back in time, witnessing the evolution of stellar populations and the chemical enrichment of the cosmos. Each galaxy, each cluster, each nebula is a record of the ongoing story of stars, a narrative that spans billions of years and countless generations. Galaxies also interact in clusters, superclusters, and the long filaments of the cosmic web. Stars are affected indirectly by these large-scale structures as galactic interactions trigger starbursts, compress gas clouds, and redistribute stellar populations. Tidal forces stretch galaxies, creating streams of stars that illuminate past mergers. In some cases, interactions strip gas from galaxies, quenching star formation, while in others collisions trigger intense bursts of stellar creation. The universe is alive with these processes, and stars are both participants and witnesses. Even in low-density environments, stars play a role in shaping the interstellar medium. Stellar winds from isolated massive stars carve bubbles into surrounding gas. Supernova shock the medium, compressing clouds or dispersing gas. White dwarfs in binaries produce nova, injecting energy and elements. Every star, regardless of environment, contributes to the ongoing cycle of matter and energy, influencing regions far beyond its immediate neighborhood. Cosmic recycling ensures that every generation of stars benefits from the legacy of its predecessors. Metals forged in massive stars are returned to the interstellar medium, incorporated into subsequent generations. Stellar remnants, white dwarfs, neutron stars, and black holes remain as enduring markers of past generations. The interstellar medium itself, enriched and shaped by these processes, becomes the womb for new stars, continuing the cycle across billions of years. By studying stellar populations across different galaxies, astronomers reconstruct the history of the cosmos. Metallicity gradients, age distributions, cluster populations, and galactic dynamics provide evidence of past mergers, starbursts, and quiescent periods.
Stars are the tracers of cosmic history, encoding information about both local and universal processes.
Their light, traveling across millions or billions of light years, carries the fingerprints of nucleosynthesis, gravitational interactions, and galactic evolution, allowing humanity to read the story of the universe written in starlight.
Even the faintest stars have significance. Red dwarfs, though dim, are the most common stars in galaxies, their long lifespans preserving chemical history.
Brown dwarfs, substellar objects, act as markers of star formation efficiency.
White dwarfs record the history of intermediate mass stars.
Neutron stars and black holes mark the deaths of massive stars and continue to influence galactic dynamics. Together, these stellar populations form the backbone of galaxies, linking structure, chemistry, and energy flow. The cosmic web, the vast lattice of galaxies stretching across billions of light years, is illuminated by the cumulative effects of countless stars. Clusters of galaxies contain hundreds or thousands of galaxies, each filled with stars cycling through birth and death. Filaments connecting clusters are home to smaller galaxies, their stellar populations interacting through tidal forces and mergers. Voids, sparsely populated regions, contain isolated galaxies whose stars evolve slowly. Across this structure, stars are the threads that illuminate the cosmic tapestry, connecting the small-scale physics of fusion to the grand scale of the universe itself.
Among the most dramatic stellar environments are starburst regions, where galaxies or galactic nuclei experience intense concentrated star formation. In these zones, gas densities are extreme and stars form in rapid succession.
The Antennae galaxies, emerging pair located 45 million light-years away, exhibit hundreds of young star clusters, each containing thousands of massive stars.
Radiation, pressure, stellar winds, and supernova interact in complex feedback cycles, regulating subsequent star formation while enriching the interstellar medium.
Starburst regions demonstrate how galactic interactions can dramatically accelerate the cycle of stellar birth and death.
Supermassive black holes residing at the centers of most galaxies influence star formation on both local and global scales.
Accretion of gas onto these black holes produces active galactic nuclei AGN, emitting prodigious amounts of energy across the electromagnetic spectrum. Powerful outflows and jets from AGN can suppress star formation by expelling gas or trigger it by compressing surrounding clouds.
Observations of galaxies, such as M87, reveal jets extending thousands of light years, reshaping gas dynamics and illustrating the intimate link between the smallest and most extreme objects in the universe and the lives of ordinary stars.
Within galactic disks, the interplay of gravity, turbulence, and magnetic fields produces intricate structures where stars form. Spiral arms act as compression waves, concentrating gas and triggering star formation along well-defined regions. Molecular clouds collapse into protostars, often in clusters, while nearby massive stars illuminate the clouds in spectacular H. Raman II regions. The Carina Nebula and the Orion Nebula are prime examples where ultraviolet radiation from young stars sculpts gas into pillars, cavities, and filaments, creating breathtaking visual spectacles while driving the ongoing cycle of stellar birth. Dwarf galaxies, though smaller and less massive than giants like the Milky Way, provide critical insight into galactic evolution and star formation.
Their low metallicity and shallow gravitational potential wells make star formation more episodic and sensitive to feedback. Observing dwarf galaxies in the local group, such as the Large and Small Magellanic Clouds, reveals that even modest environments can host intense star-forming regions. These galaxies preserve chemical signatures of early star formation and provide clues to how the first stars influence subsequent generations across the cosmos.
Globular clusters are microcosms of galactic evolution. Dense spherical assemblages of stars, globular clusters contain populations that are nearly as old as the universe itself. In clusters like Omega Centauri and 47 Tucanae, astronomers can study the chemical composition, ages, and dynamics of stars formed in the early universe. Close stellar encounters and binary interactions are frequent, producing exotic phenomena such as millisecond pulsars, blue stragglers, and X-ray binaries.
These ancient systems preserve the story of early star formation, giving context to the evolution of galaxies over billions of years.
Stellar feedback is a critical regulator of galactic evolution.
Massive stars inject energy and momentum through winds and radiation, while supernovae deposit heavy elements into the interstellar medium. This feedback can trigger new waves of star formation or inhibit it, depending on local conditions. By balancing energy input and gas compression, galaxies maintain star formation rates that evolve over cosmic timescales. Observations across the electromagnetic spectrum from infrared to X-rays reveal these processes in action, showing how individual stars collectively shape the evolution of entire galaxies. The large-scale structure of the universe, defined by clusters, superclusters, and filaments, is illuminated by the cumulative effect of countless stars. Galaxies interact within these structures, merging and exchanging stars and gas. Stellar populations trace these interactions, allowing astronomers to reconstruct histories of cosmic formation.
Streams of stars, stripped from satellite galaxies, reveal past mergers, while supernova-enriched gas fills intergalactic space, linking stars in one galaxy to the material that will form stars in another.
In this way, stars operate not only as individual engines of energy and chemistry, but as connective tissue across the cosmos. Cosmic evolution is visible through the distribution and behavior of stars across billions of years.
In the early universe population, Roman 3 stars, massive and short-lived, ignited the first light, enriched the primordial gas, and seeded subsequent star formation.
Observations of high-redshift galaxies reveal intense star formation and rapid chemical enrichment, illustrating how stellar processes shaped the universe within its first billion years. Over time, star formation shifted to more moderate rates, producing long-lived stars that dominate modern galaxies, ensuring continuity in chemical enrichment and structural evolution.
Even within relatively calm galaxies, stars influence their surroundings profoundly.
Supernova remnants expand into interstellar space, triggering compression of nearby clouds, initiating new generations of stars. Planetary nebulae illuminate the interstellar medium, contributing carbon, nitrogen, and oxygen for future planetary systems. Compact remnant neutron stars and black holes interact gravitationally with other stars, affecting their orbits and sometimes producing dramatic events like X-ray flares or gamma-ray bursts.
Every star contributes to a dynamic, interconnected galactic ecosystem.
Stellar populations reveal the chronology of cosmic history. Age, metallicity, and distribution of stars across the galaxy provide insight into past events, mergers, starbursts, quiescent periods, and feedback cycles. Observing these populations across multiple galaxies allows astronomers to compare evolutionary paths, revealing universal patterns of star formation, enrichment, and dynamical evolution. Stars thus act as both agents of galactic evolution and archivists of cosmic memory, encoding the processes that shaped the universe over billions of years. As galaxies evolve, their stars continue to shape the future of the cosmos. Gas expelled by stellar winds and supernova becomes the material for new generations. Stellar remnants persist, influencing galactic dynamics and sometimes merging to form gravitational wave events.
Young star clusters seed future stellar populations, while massive stars continue to illuminate and energize their surroundings.
The interconnected cycles of birth, life, death, and regeneration ensure that the story of stars is continuous, linking past, present, and future generations in an unbroken chain across space and time.
The grandeur of galactic evolution, illuminated by the light of stars, underscores a profound truth.
The universe is a tapestry woven from stellar processes.
Every galaxy is a theatre, every nebula stage, every star a character whose actions contribute to a larger narrative.
From the earliest population Roman 3 stars to the ongoing formation of red dwarfs in distant spiral arms, stars define structure, drive evolution, and connect the cosmos in a luminous web of energy, matter, and time.